Well, hello. Hi, I'm Philip. I'm going to tell you for the next 45 minutes or so how to make your data fabulous. Though there is a second meaning to fabulous, we'll get into that in a moment. So let's get started and see where we can take this. I'm a developer advocate at Elastic, the company behind Elasticsearch, Kibana, Beats, and other products. Um, Obviously, I have a bit of a view from how to make your data fabulous in Elasticsearch, but what I'm going to show you and tell you is much more broadly applicable. It's generally a bit of a dive into trade-offs in data, but you'll learn more in a moment. So this is what we're using at Elastic, and we might run into this once or twice during this presentation. But like I said, it's generally a much more broader talk. So what is the perfect data store solution? And if you ask that people, they will give you various answers depending on where they stand. I think the right answer to that is always it depends, which is also one of our favorite answers at Elastic, because in a complex system, there are always lots of trade-offs. So there is normally not one straightforward single way to do it, but it's just a combination of trade-offs. And we'll focus very much on these trade-offs today. As I've said, you need to pick the right trade-offs to make it work for your system. And while some try to sell you or convince you that there is magic, I always doubt that there is magic in that way, that stuff will just work and everything will be great. So talking about trade-offs in data stores, I assume many of you have heard of the so-called CAP theorem: consistency, availability, and partition tolerance. For those of you who haven't or just vaguely remember anymore, quick refresher. So CAP is actually based on a paper, and that paper in turn is based on a talk. So Eric Brewer from Google gave a long time ago that talk, and then Tess Gilbert and Nancy Lynch wrote this very well-known and relatively straightforward and simple paper, which is called Brewer's Conjecture and the Feasibility of Consistent, Available, and Partition-Tolerant Web Services. And it doesn't just mean web services, but it means any distributed system. And I'll mostly look at data stores because they are one of the poster child or children of distributed systems here. And we'll look into like what consistency, availability, and partition tolerance are. And those three together make up the so-called CAP theorem. So you have consistency, which is the total order of all operations, that each operation looks as if it were completed at a single instant. So you have a distributed system with various nodes or things that work. And operations come in from all the sides. Yet still, if you want to have a consistent system, there is a total order of all of these requests coming in. So it's pretty much like you have a single instance, and then it's like one after the other. It's like a nicely ordered queue where one after the other walks through the system. Even though the system might be much more complicated, you want to have that total order so that it's very clear what operation is based on what other operation. So for example, if you have an increment and a decrement, it needs to be clear in what order they are being applied, so that even if you query between the increment and the decrement step, you always get a consistent view of what is the current state of the data over all your system. Even though they even out after being both applied, if you first add, then query what is the current state, and then detract again, at every point in time, you want to get the correct result based on that total order. That is consistency in a temporal sense, that one operation runs after the other, and you always have a consistent state. Then availability is that every request received by your system in a node that is working must result in a response. This sounds pretty obvious and like, why wouldn't it? So the thing that this is not possible with availability is that a node says like, there's a weird state in the cluster right now. I'm not quite sure. I will not respond. So every working node needs to respond to every request. That is what availability means here. And then you have partition tolerance, that the network will be allowed to lose arbitrary messages sent from one node to another. That sounds very harsh and strict, But in distributed systems, this is a thing, it happens. And your system still needs to keep working. And what the cap theorem basically says is like you have these three attributes that you want to have. At most, you can have two at any point in time. So you can see here, these are the three attributes that you might want to have. There is no middle ground where you have all three. You can only choose between a combination of two, which is, by the way, not guaranteed. If you have bugs or a poorly designed system, you could have only a single attribute. Or you might not have any of them if you have too many bugs and stuff just doesn't work out. But at most, you can have two. That is what the paper is basically saying. And there are two misconceptions here that are common. The first thing is that some people are like, well, our data center or our infrastructure is so good, we don't have partition tolerance, or our network cannot separate and break apart, which is not exactly true. The big cloud providers have a while ago published a paper, or various stories as well, how many nodes, racks, entire availability zones or data centers they lose on average a year, and it's quite a few. If you say like, we don't have that in our system, it's potentially because your monitoring is not as good, and you're just missing any small outages, or you have been exceptionally lucky, and your luck might run out at some point. But generally, stuff breaking, networks falling apart, routers dying, whatever you have, those are things that will hit you sooner or later. The next, or the second big misconception here, is that consistency, unfortunately, is an overloaded term. And you have ACID in the transactional sense, the atomic, consistent, isolation, durability, these transaction attributes that you have in a database transaction, is a different consistency here than the consistency in the cap theorem. So in the transaction, the consistency is from one logically correct state to the next. So it's basically after one operation, your not null constraint is still valid. Your referential key is still has integrity. So consistency is really a predicate that they are moving from one correct state to the next. Whereas the consistency in cap is a linear order. So it's basically saying that how things or how operations are applied has a linear order, and that is the consistency in the system, which is a bit unfortunate that there are two, and they mean different things. But ACID has a different meaning of consistency than cap. And if you want to explain that to your kids or your parents, there is this nice story of how to explain the cap theorem, also because the paper is generally quite simple, so you can just read it. But if you want to explain it to your parents or kids, you can also have this story, which I like, around Robinson Crusoe. So Robinson Crusoe is on his island. So he's partitioned from the rest of the world. And then a ship comes by and asks him a current question, like, who is the king or queen of England right now? And then Robinson Crusoe, he is partitioned from the world, so he has the P of partition tolerance. And when he's being asked, he has to decide, am I consistent or am I available? Because he has been partitioned for a while, so he might not know who is currently the king or queen of England. So he can either answer, then he's available, and then he might give an outdated answer, so he is not consistent with the rest of the world, or he doesn't answer, so he is consistent, but he's not available because he is not answering. So even Robinson Crusoe on his island where he's separated, he could have this problem of consistency, availability, and partition tolerance that you can only have two. Or to explain it more in IT terms, it could be that you have, let's say you have a cluster of 3 nodes and the network breaks in the middle. So you have one node here and 2 nodes here, and they currently cannot talk to each other because in between where I'm basically, there is like the network partition. And then you write to these 2 nodes here, and then this other node down here has to decide again, am I consistent or am I available? Because it could keep answering queries, then it's available, but it's not consistent with the other 2. Or it could stop answering even though it's running, then it's consistent, but it's not available because it's currently not answering. So that is the entire proof of, or that is how constructive the paper actually is, or how it's being explained. And if you have recognized the island in the background, that was the one from Star Wars. And I will show you a couple of things based around Star Wars, or will base most of my examples around Star Wars. So since that has been a while, I guess not many of you have recognized this island in the background anymore. At least I wouldn't. So I stopped asking now because it's kind of an unfair question. But we will build a lot of our examples here around Star Wars. By the way, you can break the cap theorem by something like def null, where you always throw away all the data. So it's always consistent and it's always available and it works in partition tolerances. But that doesn't really make it a useful system at the same time. So while you can in theory break cap, that's not a useful system after all. Okay, that was the cap theorem that is widely known and is one of the best known trade-offs where it's like 2 out of 3. At Elastic, we have the so-called FAB theory, where it's kind of like the same approach, 2 out of 3. And we have 3 different approaches here. The FAB theory was created by our colleague Mark Howard, seeing him at doing his favorite hobby. And the 3 things that he described that you want to have are fast, accurate, and big. So that's FAB. Fast is you want to have operations that are near real time instead of batch processing, which basically means you run a query, you wait for the result, you don't go for a smoke or a coffee in between, but it's fast enough that the human waits for it. Let's stick to that simple definition. Accurate, you want to have exact results rather than approximations. That also sounds pretty obvious. Why would I even want to have approximations? And finally, big, you need to parallelize or distribute over multiple nodes to handle all the data, either because the volume in queries is so large or the amount of data is so large that you cannot hold it on a single system or a single node. So that is the big, you need to scale out horizontally. And I assume the fast is pretty clear. A human can wait for it. So it's probably like a second maybe, or 5, depending on what your patience is. But it's not minutes. And parallelizing is pretty simple because it needs to spread out over multiple nodes. I don't want to get too much into the big data discussion because big data has been a term that has been used and abused way too much. So let's skip that and let's say simply what is spread out over multiple nodes. That is what we mean with big here. So fast is clear, big is clear. How about accurate? What even would be a useful system that is not accurate? And we'll dive into that and see how that works. And my example will run through Elasticsearch because we have a couple of trade-offs where we are fast and big, but not necessarily accurate. Accuracy is a trade-off that you can pick in your system. The only thing that you need to know about Elasticsearch, the unit of scale is a so-called shard. So you have your data and it's broken up into multiple so-called shards, and those can reside on different nodes. So that is what allows us to have this big approach to spread out the data over multiple nodes. That is a shard. Does anybody know where the term shard is coming from? Because it's quite widely used. I think MySQL and various other NoSQL data stores use shard for that splitting of data as well. There are probably multiple theories. The one I believe in, if anybody remembers this one, if anybody is really old, you might have played this game back in the day. And yeah, by today's standard, it looks pretty horrible, but that was Ultima Online. And so what this did was there was an evil wizard, and sorry that this is cut off right now. And that wizard wanted to gain control over the world and kind of like put the entire world into a crystal. And then that crystal was shattered. And then you had these so-called shards, part of the game that you could play individually. So that is where the term shard was coming from. At least that's the story I believe in, and lots of systems have adopted the shard system, and that's kind of like the background story to that. So term segregation. Anybody remembers the term segregation? So I have multiple terms and I want to know which term appears most frequently in my dataset. And on a single node, that's quite easy. But let's assume we have 1 million different terms and we have spread that out over 10 nodes. Do you really need to build the full list of the 1 million terms on each node, then combine all of them to figure out what are the most common terms? Because that would be a very big calculation. It would be pretty slow. You need to transfer a lot of data. It probably doesn't fit our fast attribute anymore. My sample here will be a bit simpler than millions of documents. I'm using the most common words of the historically very first Star Wars movie. So back in the days, the very first one that came out. And somebody luckily did the counting for me. So it says, or that Luke appeared 64 times in the movie, R2 31, Alderaan 20, Kenobi 19, etc. So what I'm doing is I'm storing 64 documents with Luke's, 31 with R2, etc. And then I want to run this term segregation to basically find out again that Luke is the most common term and appears 64 times. What I'm doing here is I have my index, which I call Star Wars, with these documents, and I have split it into 5 so-called shards, so into 5 pieces. So my data is broken up into different sets. Let's see how that works live. So I have the current version of Elasticsearch running. That's not so interesting, but just to make sure it's working, I can search for the term Luke. And like I've said, we can see here we have 64 results, and one document that I've stored looks like this. So we have 64 documents that look like this, Luke. All of them got a random ID. They're in the index Star Wars, and I can easily find them. So now I want to run the terms aggregation. So here, this is an aggregation. I gave it the name most common because I'm looking for the most common term. And then I say, I want to use this word. And I want to have just the top one. So it's basically like a limit 1 in SQL. So I only want to have the most common word returned to me. That size 0 down here means I don't want any of the actual documents returned because I don't care for these Luke documents. I just want the total count. And the answer that we expect is 64. If I run this, let's see what we get. And the answer that I'm getting is that we have 60 Lukes. And you might be confused, like, how can we calculate so badly? I've documented these, and you could also visualize that, but it doesn't really matter. And you might say, this is not possible. It's not true that there are only 60 Lukes. Something went horribly wrong. And you are correct. Something went horribly wrong, and we need to figure out why. And here we have the FAB theory in action already. And let me zoom out a bit of my slides. I'll run the code live. I'll only show you a couple of things taken out of the slides. So what is important here is I have cheated a bit. I've prepared my data in a way that we actually run into this problem much sooner than you normally would. So there is a so-called routing key in this data which defines into which shard my documents are being written. And the first 10 looks went to random documents, but the remaining 54 looks were all written to the same routing key and ended up on the same shard, which the calculation is basically the shard number to which I write this is I hash that routing key, calculated modulo the number of primary shards, and this gives me the shard number. Why do I hash it? So that data is generally evenly distributed based on the information. And normally that would use the ID, and my randomly generated IDs will hash very nicely out, and all the shards will have the same amount of data, so everything would work. In my example, I have skewed the data so that most of them are going to the same shard. And now what you can see here is that some shards have a lot more documents than other shards. And why this is relevant is because the term segregation doesn't get the full list of documents of all terms, but only the top few terms. And I've skewed the data in a way that the top results might not contain Luke in some shards. So that's why we're missing some Lukes in our results. So how the term segregation is actually calculating this, it's taking size, how many documents do we want to have returned, which was 1, because I only wanted 1 document back, times 1.5 plus 10. So I have 1 times 1.5 plus 10. This will be rounded down, if I remember correctly. And then you add 10. So here you would get the top 11 results per shard. This is how many sub-results per shard we were calculating for a top 1 calculation. And I've basically made sure that Luke is not in the top 11 on all the shards, so we're missing a couple of Lukes. And that's why we got that result. This is just for illustrating the problem. If you have evenly distributed data, you probably would, or you wouldn't have run into this. Then this default shard size would have worked for you, but I've kind of like constructed the example a bit that you run into the problem. And then in the result, you also have a couple of other pieces of information. So it says the other documents that were not Luke were 228, and it also calculates the total error bound for this overall calculation as up to 10 could be missing or wrong. So basically, it knows of the 11th result. It knows how many documents you're missing. And then that gives you the error bound. You can also add this attribute here, which shows you the error count just for this keyword here, or the word that we're calculating, which will then tell me that, okay, we have 60 looks found, and the error bound could be, there could be 4 more, which is actually the right one here. How does it do that? In every sub result where Luke is not included, it knows what was the 11th result, and it knows there could be a 12th result with just as many hits, and then it would add that to the error count. So I assume on 2 shards or so, we didn't get the Lukes back because they were not in the top 11. And then the 11th result had probably 2 each as the 11th result. And then it said like, well, so there could be 4 Lukes missing. And that's how we figured that out. What you can do is you can manually set that shard size to 20. So before it was 11. And the shard size is then getting you 20 sub results for each shard. So you're trading a bit of fast for accuracy, because this will be slower. You have more sub results to calculate on each node, and then you have to combine them, but your results will be more accurate. And if I run that, since I only have like 18 or 16 terms in total in my document, this will now be correct. And you can see now I found 64 looks, 0 error here. It also got overall 0 errors. So this is the correct result in my data set that I have been getting. And that was the first example for that fast, accurate, and big trade-off. You could see at first we were faster but less accurate. Then I traded some accuracy for some speed. That was the first example. I have another one. So we have the cardinality aggregation. Cardinality aggregation is like how many unique terms do you have in your data set. And there are multiple ways to calculate that. The naive one would probably be something like a hash set, where you have, which is a data structure where based on the hash value, you would override the previous word. So if I hash Luke, it would always give me the same hash, and I store it under that hash. And then I would just override this, or this Luke is overwritten by this Luke. This has, however, 2 downsides. First, you need to run this for every single term. If you have a couple of million terms, this will be a lot of calculation. And B, this will grow linearly in terms of memory size, with the number of terms, of unique terms that you have. So if you have a couple of million terms, this will need quite some memory, which then brings the problem. What if your data store then runs into an out-of-memory exception because of that? Because you ran a unique term segregation or cardinality aggregation on such a large data set that it kills your node. So this naive implementation is nice, but it doesn't really work or scale. And we'll get back to how to count with some threshold of accuracy in a moment. If I flip a coin, what is the chance that I have 3 heads in a row? And we'll use this for an estimation of how many unique terms we have in a moment. So if I want to have that, it's like 1 divided by the number of options. So let's assume the coin can only have 2 outcomes and it won't like sit on its like this thin side or corner. So it can only either be head or tail. So 2 options to the power of the number of how many times I throw the coin. So 2 to the power of 3. So it's the chance of 3 heads in a row would be 1/8. Or generally 1 divided by the number of options to the power of how many in a row you want to have. And we can use this for a so-called estimation or even so we're using an even distribution. And what we're doing is we're using a hash function, and the result of the hash function is a value between 0 and 1. And we always remember the smallest value. So I hash look, it's 0.44. I will remember this one. I hash R2, I see it's 0.71. I forget that one, I keep this one. I hash Jedi, I get 0.07. So this is the newest lowest value, and I will store this one. So you still need to hash every single value, but you only need to store one single value in memory, so it won't make your heap blow up. And what this then does is I estimate the cardinality by saying 1 divided by the minimum value. So 1 divided by 0.07 is 14. So this would say that I have potentially 14 unique values, because the assumption is that the values are evenly distributed over my data set. And this is approximately how many unique ones I have. You can make this more complicated, or let's not say complicated, but you can switch that to IT terms. And here we count leading zeros. So basically I hash something, I have the binary representation, and I count how many leading zeros I have. And again, this is pretty close to the coin throw that I've shown you or described before. You count how many leading zeros do I have, like I have up to 3 leading zeros here. So 2 possible options in zeros and ones to the power of how many leading zeros, for example, I have. It's 1/8. So this would be the calculation of how many potential values I have. And you can see here, this is 8 values. So by just counting how many leading zeros and counting from the right-hand side I can do an estimation of how many unique values I have in my data set. And you can make this a bit more interesting. And there's a paper for that, and it's called log, and it's probabilistic averaging, and it's doing a neat trick. So it's, rather than using one log function, and then it's kind of like it has a lot of steps and it's pretty broad, that bell curve where you're trying to approximate. What you're doing in log basically is you're combining multiple hash functions. And that combination of hash functions, so you even out over the multiple hash functions, gives you this much steeper and more accurate approximation. So this is the true cardinality. And depending if you just use one hash function or multiple ones, you could get closer or further away from that result. And this is the paper that I'm referring to, log. It has then been improved by Google to go to log++. I'll show you the paper in a moment. But just to map this back to our data set that we have, let's say, how do we have these multiple hash functions? So we could use multiple hash functions, but this would be expensive. What we're doing instead is we're trying to group them randomly and then even out those random groups or buckets. So I'm hashing loop. Let's say this is the binary representation of that hash function. It's not a real one, it's really made up, but doesn't matter. So I'm taking the first 4 bits as the so-called bucket. This is 4. And then here I'm counting the leading zeros from the right-hand side. So my 4th bucket has 3 leading zeros. My 9th bucket has 4 leading zeros. My 0th bucket has 1 leading zero. And then what you do is You calculate based on the maximum number of leading zeros, you calculate how many unique values approximately do you have per bucket. Then you even it out over all the buckets, and that's your estimation of how many unique values you have. And you only have up to 16 values that you need to store. So for each bucket, you store the maximum numbers of leading zeros. And that's all the data you need to keep in memory. So it's much reduced in terms of memory use. Excuse me. And this is then the pseudocode if you put this together from the paper. Like I said, Google improved this. It called it hyperloglog, and then it was changed to hyperloglog++ after another refinement. They basically it kept the same principle. It just reduced the error bound a little bit. And that makes your cardinality aggregations go very fast and mostly accurate. It's a bit like this scene in Star Wars. So how to run this and how to see how this looks in practice. So I run my cardinality aggregation here on my word field, and I say the precision threshold I set explicitly to 10. This basically means up to 10, I will do the hash-based or the unique value counting approach. For higher values, I will use this probabilistic data structure. Again, I'm not returning any documents, but I want that very low precision. And when I run that, it tells me that I have 17 unique values in my data set, approximately. I think it's 16 if I remember correctly. So it's off by 1, but it needs very little memory here. What we have is the precision threshold. By default, we would use a value of 3000. You can set this up to 40,000, so that would be accurate counting. And over that, it's always an approximation. I've only set it to 10, so it's very tiny. But otherwise, my data set would have been too small to actually show the errors. So below, you have linear counting in a custom set, and otherwise, you have hyperloglog++, so it's the approximation. And basically, how much memory you need is you need the precision threshold times 8 bytes. So in my first example, we used 80 bytes in memory for that calculation. So it's really minimal in that regard. And here we have plotted out based on the threshold value. And weirdly enough, we haven't plotted it out for the default threshold value of 4000, but we have only taken 3 other values. But at least it's powers of 10 that we have tried out here, so you get an approximate idea. And you can see, based on the number of unique values, how close is our approximation. And you can see, if you use a threshold of 10,000, the error bound is only once here going over 1%. But otherwise, we are, even for very large numbers, we are very close. However, if you only use a threshold of 100, you can see you can have an error of, I don't know, up to 5% or 6% or so. So it's really a trade-off between how fast or with how little resources do you want to make this aggregation work, and how accurate do you want to have it. So it's really accurate and fast as a trade-off where you have basically a lever that you can put to different points. And if I run this with a threshold of 12, so now we would use 96 bytes for this. You can see we're already getting the right calculation where we get 16 values back. We have 10 minutes left. I have one more example. Before I jump into the final example, there's always the question, or sometimes the question, should we pre-compute the hashes? So there is a way to actually do that in Elasticsearch. Pre-compute the hashes, does it make sense or not? What is the answer? It depends. So for large and high cardinality fields, it could make sense if you run lots of cardinality aggregations. If you have low cardinality aggregations or numeric fields where the CPUs are very fast to hash them, it generally doesn't make sense to calculate or pre-calculate the hashes. There was, by the way, an improvement that was called log beta. We tried to implement it. It didn't make any improvement, so we threw it out again. There is a new paper that's called hyperloglog sketches. We haven't implemented that one yet, Maybe this one is more accurate with the same amount of memory, so this could make a difference. We just didn't get around to implement it yet. But if you're very keen on that, that would be the paper to see how that works in detail. Okay, then we have the inverse document frequency. So if I search for Luke, and that is kind of like the core strength of a search engine, that you rank or sort documents based on their relevancy. So here I'm doing what you do in full text search. I search for Luke, and then you see I find my 64 Lukes. So this is good. But you can see this Luke here is very relevant because the score is basically the relevancy. You can see this same Luke here is less relevant. And then as I scroll down in my results, you can see these Lukes are much less relevant. Why could the same document be more or less relevant in my data set? And that is, again, because it's a distributed system and there is a little shortcut that we're taking here. So let's see, for the last, how many minutes do we have? Like 8 minutes or so. What is going on here and why is this still wrong? What we're using in the background is called TF-IDF, term frequency, or in inverse document frequency. Or the current implementation of this is BM25, which stands for best match, and is the 25th iteration of that best match algorithm, which has been the default in most full text search engines for a while. So it's based on three things, basically. It takes the term frequency. So how often does my search term appear in a document? The more often it appears, the more relevant my document is, probably. And you can see here, this is how many times, for example, if you search Luke and Luke appears once in a document, it's that relevant. If Luke appears 5 times, it's more relevant, or this document is more relevant. You can see the main difference between TF-IDF and BM25 is that TF-IDF is just a square root, and keeps growing indefinitely. BM25 is basically like, once the term appears 5 times in a document, it's not getting much more relevant anymore. So that's the term frequency. Then we have the inverse document frequency, which basically says if you're searching for terms and they appear very rarely over all your documents, the rare stuff is more important than the common stuff, which would look something like this. If Luke appears a couple of times, it's very relevant. If Luke appears hundreds of times, it's not so relevant anymore. So rare stuff is more relevant. And then finally, the field length norm is if your search term appears in a short field like the header, it's much more relevant than if it appears in the long text body, because it's kind of like in the middle of a lot of other terms, so then it would be less relevant. So it's 1 divided by the square root of the number of terms. And then you need to know how Elasticsearch actually fetches data. So let's say we have a node. So the request is coming in. This node coordinates my query, and my data is, let's say here, split out over multiple shards. So we have primary and replica shards. Let's forget those for the moment, but it's just like 0 and 1. And then basically this node queries my nodes for the data, and each node again gives you back the sub result. What problem do you already see in TF-IDF? The term frequency is the same, but the inverse document frequency depends, because on some of these nodes, the Lukes are much rarer than on others. And that's why our results are so off. So what you first do is you run this query phase. We call it query then fetch, or scatter gather. With a query then fetch is basically, in the first step, you query each shard and say, give me back the best 10 documents, for example, if I want 10 results to have. You send back the list of 10 documents with their score and ID. And then in the second step, you actually fetch the 10 best documents. So it could be 7 here and 3 here. But there is no point or need to transfer 10 documents from each shard, especially if you have a lot of shards in the first place, but it's only fetching the actually relevant documents. And you could change that. You could add a step before that, which is called DFS, distributed frequency search, which at first goes to all the shards, says like, how many Lukes do you have? And then for the next one, for the IDF part, averages out the statistics of how many loops there are globally. So then you have the same relevancy for all the loops. So here I'm adding this parameter. So it's adding not just a two-step search approach, but now I have basically a three-step search approach that I'm running here. And now you can see all the loops have the same relevancy of 1.5. So we have evened it out. So we have solved that one as well. It was easy. The main question we then get, like, how much does this cost us in performance like the others? And there again, the answer is always, it depends. Like you can see in my example here, under similar conditions, I'm testing two different scenarios. And yeah, the scenarios are the same, but it's a different trade-off because the squid is doing much better underwater than the house cat. And this is whenever somebody is doing benchmarking with different scenarios or different products, that one might behave much better under these circumstances than the other. So you get these skewed results. And then the question is, should I always use DFS, query, then fetch in production? And the answer really is, it shouldn't be required, because only in my data set where the looks are so unevenly distributed, it is a problem. If your looks are distributed evenly, you shouldn't have that problem. And then you could have the approach that is also the default in Elasticsearch 7 or since then, to use a single shard. What do we give up then? We basically not entirely give up on the big, but we reduce the big because it's only one node that can hold the data. It will still be fast, it will be accurate, but it will not be as big. And now I can actually run through these examples. And what I'm doing here is I'm taking my Star Wars index, shrink it down to a single shard so it's not distributed anymore, and store it in the Starlet Wars, so the little Star Wars index. If I run my search aggregation without DFS, query, then fetch, this one now is actually accurate because it's a single shard. The inverse document frequency is always the same. So this one gives me exact results. It's not scalable across multiple nodes anymore. If I run a term segregation, this one by default is again exact now because it's getting the top 11 results on a single shard, and that will include the top one result that I'm getting here. Only the cardinality aggregation would not make any difference based if you have one or more shards, because it's still using the estimator if it's bigger than the accuracy setting that you're applying. So this is what we're doing here. And Simon, one of the Elasticsearch co-founders, always says, use a single shard until it blows up, because it's potentially faster and it is also potentially more accurate depending on your use case or the aggregation that you're using here. So this was kind of like easy, but it's kind of also a cheap trick to reduce it down to one shard because we've given up on the big now. So you will really need to find the right trade-offs that make sense for your system. So to wrap up, it's all about the trade-offs in your distributed data store. What do you need? How much fast, accurate, and big do you need? Which attributes in the CAP theorem do you want? By the way, if you don't pick those explicitly, the system will basically pick or have something built in for you, and you will just find it out as a surprise later on. So you should make those decisions explicitly. I hope you've learned something both about the CAP theorem and the FAB theory. FAB doesn't have a fancy paper, at least not yet. It's just a theory that we have, but I think intuitively it makes a lot of sense that you have this fast, accurate, and big, and you need to kind of like trade some for the others. And that's it. If you have any questions, I will head over to Slack after this to answer. Hope that makes sense for everybody, and enjoy the rest of your conference. I think we're finishing just like 30 seconds earlier. So thanks a lot for joining. Thanks for having me. Rustam, it was good to see you in chat, and enjoy the rest of the day. Thanks. Bye.